light energy into chemical bond energy. The synthesis part of photosynthesis is about the production of carbohydrates. So the photo part is going to involve light energy captured by photosynthetic pigments of the plant. And these photons of energy will be converted to chemical bond energy in the form of NADPH and ATP. If these molecules and the concepts of oxidation and reduction are really foreign to you, please check out my video on redox reactions. I will put the link in the description box below. These high-energy molecules are going to be used as energy sources to fix carbon, atmospheric carbon, into carbohydrates, not into glucose directly, but into molecules that can be used to make glucose. So basically what we do is we're going to divide the processes of photosynthesis into the light capturing part, which conveniently are called the light reactions, and then the carbon fixation part, which we refer to as the Calvin cycle or the light independent reactions. So let's talk about light first. Here's the electromagnetic spectrum. There's a teeny tiny little slice in there that is actually visible to us, and that's the same sliver that plants can use for photosynthesis. Now, how plants capture this light is with pigment molecules like chlorophyll A. Here's chlorophyll B. There are other pigments, though. This is beta-carotene. Beta-carotene is what gives things like carrots their color. Now, what you can do is look at the absorbance spectra of different pigments, and you'll see that they all peak in different places. And this actually allows photosynthetic organisms to be very efficient in their capturing of different wavelengths. But most photosynthetic pigments have a low in absorbance right around here. And that, as you can see in the color bar below, corresponds to the color green. So plants do not use green light very efficiently at all, and that is why green is transmitted and reflected, and that's why plants appear green. You can actually extract chlorophyll yourself in your own kitchen. I like to use spinach. You're going to need a blender and some cheesecloth, and you're going to need to blend it up not in water, that won't work, but in an organic solvent like pet ether, acetone, methanol. I know you got that in your kitchen. Don't drink this smoothie. If you filter it through the cheesecloth, you're going to get a nice solution of chlorophyll, and what you can do with it is shine light on it, and you're going to see something really cool. It's going to glow red. And this is called fluorescence. And in order to understand the light reactions, it's actually important that you understand why chlorophyll fluoresces when you shine light on it like this. So here's what's happening. If you isolate a chlorophyll molecule and you shine light on it, what's going to happen is electrons at the center of the chlorophyll are going to increase in their energy state. They're going to get excited. Oh, I like that. It's very exciting. Now, as you know, anything that goes up must come down. And in an isolated chlorophyll molecule, there's nowhere for those electrons to go. So as soon as they get excited, they immediately fall back down to what we call the ground state. And when they do that, they give off some energy in the form of heat and light. And that light we call fluorescence. And that's why it glows. Now, if you go out into the world, hopefully you have never seen a glowing plant unless you take some very interesting medication. So plants don't naturally fluoresce. And the reason is plants capture the energy of the electron before it falls back down. So you have the striking of the chlorophyll, and just like before, the electrons in the chlorophyll molecule, they increase in their energy state. But instead of being allowed to fall back down and having all that energy wasted, the chloroplast has proteins which capture the energy of the electron as it falls, kind of like water going down a water wheel, and that energy is then used to do work. And that's basically what the light reactions are about. These chlorophyll molecules are actually organized in a complex system that we call a photosystem, and the photons of light actually bounce around until they hit a reaction center, and the whole thing is very beautiful and complicated. This is what it actually looks like with all those green blobs representing chlorophyll in there, and it's actually quite beautiful. In order to understand how this works, we're going to have to understand the structure of a chloroplast. A chloroplast is an organelle with not one but two membranes, an inner and an outer membrane, and then inside there's going to be fluid that we call stroma, and that's where all of the carbon fixation is going to happen. And then most of the chloroplast is actually made of yet more membranes that we call thylakoids, and they're organized in stacks that we call grana. So this would be one granum. And in the thylakoid membranes, this is where all of the light reactions are going to occur. So we're going to talk about the light reactions first, and then later we're going to talk about this carbon fixation. Okay, so the first thing that we're going to need is a source of electrons. The electrons come from water. Believe it or not, photosynthetic organisms use sunlight to split water. So water molecules are going to be split, and of course you're going to get out of that oxygen, hydrogen, and electrons. This is called photooxidation. What's going to happen is the electrons are going to fuel the entire system of the light reaction. So we're going to watch the electrons here in just a second. We're also going to get oxygen, and this is the source for atmospheric oxygen. And you're going to get protons. And the protons are going to contribute to the proton gradient in the thylakoid lumen that we're going to see in a little bit. That's going to be used to make ATP. Okay, so let's see what happens to the electrons. When light strikes photosystem 2, it's going to get bounced around until it hits the reaction center. And there, the electrons in the center are going to be increased in energy state, just like we saw before. But instead of the electron just falling back down and fluorescing, that electron's energy is going to be captured by proteins in the thylakoid membrane called the electron transport chain, kind of like water wheels. As the electron passes through these proteins, the energy in the electron is going to be harnessed to do cell work. So the electron is going to fall through these proteins, and the energy is going to be used to pump protons against their gradient into the thylakoid lumen. So we're creating a gradient of protons here. Now, another photon of light strikes the center of photosystem 1, and that's going to re-energize the same electron to a high energy state again. Where the electron ends up is in what's called photoreduction of NADP. So NADP gets reduced to NADPH. So you should see overall the flow of electrons goes from water through photosystem 2, through the electron transport chain, through photosystem 1, and it ends up in NADPH. Wow, isn't that incredible? What about the production of ATP? Well, that's where the proton gradient comes in. So the proton gradient comes from photooxidation of water as well as the electron transport chain, constantly pumping protons into the thylakoid lumen. Now, the protons are not happy here. They desperately want to get out, but the only place they fit is through a little slot in a protein called the ATP synthase. And what will happen is the energy of the proton going down its gradient, going in the direction it wants to go, fuels the phosphorylation of ADP to make ATP. Those are the light reactions. Now, what we're going to do is focus in on the Calvin cycle and see what all of that ATP and NADPH is going to be used for. The Calvin cycle goes by a lot of names, as you can see. Melvin Calvin, yes, that was his real name, is the person who is responsible for figuring this out. He used carbon-14 to trace carbon through photosynthesis. He wrote an autobiography about his journey, which is a nice little read, and he won the Nobel Prize in Chemistry for this discovery. The star of the show turns out to be an enzyme called Rubisco. And Rubisco is the most abundant protein on Earth. At any given time, there's probably 40 billion tons of it on the planet. And it is responsible for incorporating atmospheric carbon from carbon dioxide into an organic molecule. I know you want to know how this works. Rubisco is the enzyme that is the key to carbon fixation. That doesn't mean that carbon is broken. It just means that the carbon from CO2 is going to be incorporated into organic compounds, which will be made into glucose. This really is the key to life on Earth as we know it. So I can't overemphasize enough the importance of this enzyme. So here's what it actually does. RUBP is a 5-carbon molecule that actually cycles through the Calvin cycle, as you'll see in a minute. And the addition of CO2, that additional carbon, This carboxylation of RUBP happens because of Rubisco, and what you form is an unstable intermediate that's 6 carbons in length. It immediately gets split into 2 molecules of 3-phosphoglycerate, and this happens at the beginning of the Calvin cycle. Now, the whole of the Calvin cycle, the sum of all the reactions, looks like this. Things to notice: there's the source of the carbon that's going to be incorporated into the new carbohydrate. This NADPH, that was made in the light reactions. We need some water and we need some ATP. What's going to come out of it is not glucose. Now, a lot of textbooks will say that glucose is the result of the Calvin cycle, and that's actually not true. What you're making is G3P, glyceraldehyde 3-phosphate. That is actually the carbohydrate that gets made, and that will be used to build glucose, or it could be incorporated into storage molecules like starch, structural molecules like cellulose, or anything else that the plant needs. There are 3 phases to the Calvin cycle. Phase 1 is the incorporation of carbon dioxide to RUBP, this guy right here, and that's done because of the amazing enzyme Rubisco. Phase 2 is reduction phase, and we are using up some of the ATP and some of the NADPH that we made in the light reactions. Phase 3 is the regeneration of RUBP, and this is why it's a cycle. Okay, so let's just talk about numbers for a second. If you have 3 RUBP molecules entering the cycle, you can make 6 glyceraldehyde 3-phosphates, 6 G3Ps, but it costs you 5 of those to make the 3 RUBPs. So that's actually the cyclical part of it. The only thing that gets to leave is 1 G3P, right? Because you make 6, but it costs you 5. This is kind of confusing. So if you want to see how expensive this really is, to get 1 G3P released from the cycle, it's going to cost 9 ATPs and 6 NADPHs. So this is a really expensive process. So here is a really good summary of all of this. We're going to input solar energy and water, and we're going to run the light reactions. And the products of the light reactions include oxygen gas, right? That comes from the splitting of water, and the high energy molecules ATP and NADPH, which is going to provide reducing power. Those, along with carbon dioxide, will feed into the Calvin cycle, the outputs of which include the sugar. It's actually G3P, which will be converted into glucose. That's the chemical energy. And ADP and NADP+, which will feed back into the light reactions. Here's a